Welcome back. In this shorter lesson, we are going to take a look at some linear algebra concepts that we're going to need in order to analyze systems of differential equations. So I like to call this the linear algebra crash course. So we'll just talk about some of the essentials that we need in order to move forward. So first of all, and the most important concept in linear algebra is the concept of a vector. And we've seen some of these already, but to more formally define them, a vector is a directed line segment whose tail begins at the origin and whose tip terminates at the coordinate specified by the vector. For example, x equals, and notice how we are talking about vectors as opposed to the variable x. When you have a letter, lowercase letter with a arrow over it, that implies that it has more than one component, and we can typically think about these as the x and y components. So even though we still are thinking about this value here as the x value and this value as the y value, we can still call the vector x with an arrow over it, and that's different than what we're calling the component x. So this vector here has its tail and its tip right at this point, and you can see that it starts at the origin and terminates at the point 1, 2. Now that's in standard form. You could also have vectors that start somewhere else. For example, let's say at the point 1, 3, and as long as its displacement is 1 in the x direction and 2 in the y direction, we could say that that vector has the same that's the same vector as the one we're analyzing that's down here at the origin, that's over 1 up 2. So these are actually identical vectors. They don't have to be at the origin. We can perform operations on vectors. We can add them, we can subtract them, we can scale them. For example, if we took 3 times the 1, 2 vector, we get the 3, 6 vector. And an important thing to notice is the change in y over change in x of a scaled vector. For here, it's 2 over 1. For the scaled version of that vector, we have 6 to 3, which is still 2 to 1. So that means that the slope of this vector has not changed. It's still going to point in the same direction, but it's going to triple the length of that vector. So here we have both of those vectors plotted. We can see that the 1, 2 vector is on the same line as the 3, 6 vector, so that effectively just creates a scale effect and not a rotation of any sort. And we can find the magnitude of a vector, or the length of a vector, of x equals, let's say its components are a and b. We can write that as absolute value of x. Now, absolute value just means length of. And so even when you're talking about numbers and you say, what's the absolute value of -2? And you say it's 2, that just means that -2 is 2 units away from relative 0. And so to find the magnitude of a vector, it's equal to the square root of its components squared. To see why that's the case, if you look at this vector here and you triangulate it, you make a right triangle where its two sides are its x component and y component. This component is 1 unit long. This component is 2 units long. We can think about this as the hypotenuse, and we know from Pythagorean theorem that the square of the sides equals the sum of the square of the sides equals the square of the hypotenuse. And so c is effectively what we're referring to as the length of that vector. So because c squared equals 1 squared plus 2 squared, c is equal to the square root of the components squared. So that's how you can write the magnitude of, or we'll often call it the magnitude of a vector, but the length of a vector will suffice because we're not going to be dealing with higher dimensions where length doesn't make sense. So we said we can scale vectors, but it doesn't have to be by a constant. The scalar could be a function. So if by scalar, we just mean it's a number. And e to the 3t, even though it's a variable is still just a number. So if we scale the 1, 2 vector by e to the 3t, we're going to scale both of its components by e to the 3t, just like when we multiplied the vector by 3. So that's about all we need to know about vectors for the current moment. A matrix is effectively a collection of vectors. For example, we can write A equals 3, 1, 2, 1, and that is a matrix full of 2 vectors. You can think about them as the vectors 3, 1 and the vectors 2, 1. Now this is a matrix that has 2 rows and 2 columns, so we call it a 2 by 2, and we always say rows by columns. That's just the convention. So if I say 2 by 3, nobody ever confuses that to mean 2 columns and 3 rows. We always are in the convention of saying rows by columns. So matrices can be added and scaled as well. Whenever you add 2 vectors, you might imagine that if I took 1, 2, plus 3, 5, I would just add their components. They would have to be the same size. So this would be 4, 7. And if I were to add 2 matrices together, for example, 1, 2, 3, 4, plus 5, 6, 7, 8, that would simply be 1 plus 5, 2 plus 6, 3 plus 7, and 4 plus 8. So that's how we would add. Matrices, if we scaled a matrix by a constant, so if we took 3 times 1, 2, 3, 4, we would scale its components, and that would be 3, 6, 9, 12. So when we actually multiply, when we conduct matrix multiplication, it's a little bit strange. It's not the way we add vectors or scale vectors or even add matrices or scale matrices. You would think that they would have to first of all be the same size, but here I have a 2 by 2 matrix multiplying a 2 by 1 vector, and what I end up with is a vector that has 2 columns. The column is, remember, this is just one number. 3x plus 2y is a single number, even though it has 2 terms. This is still 2 rows with just 1 column. And the way matrix multiplication takes place in a visual form is the elements of the second matrix multiply or scale the vectors of the first matrix. So here, if you notice that this is the first element in here, if you were to tip over this vector on top, you would see that the x is going to multiply the first column, the y is going to multiply the second column, and then by definition, we're going to add those two together. So x times the 3, 1 vector, y times the 2, 1 vector, add those together. That's how matrix multiplication is defined. We get 3x plus 2y and 1x plus 1y. So already this is giving us a way to represent a system of equations where we could have a matrix that has coefficients in it and then a vector that has the variables in it that maybe we're trying to solve for. As another example, here is a system of equations that is written as a matrix equation right now. So a matrix equation just means that it has matrices and vectors in it, potentially both, maybe just one or the other. And so if we do the multiplication for this, so again, think about it this way, the first, second, and third columns are going to get scaled by x, y, and z respectively, and then those scalar multiples are going to get added together. So x times the 1, 4, 7, y times the 2, 5, 8, z times the 3, 6, 9, those get added together. Now to add that together, x multiplies all the top components, so 1x, 4x, 7x. Y multiplies 2, 5, and 8, so we'll have 2y, 5y, 8y. And z will multiply 3z, 6z, 9z. And then we're going to add those together, add the vectors. So we just add the components of the vector. So 1x will add with 2y and 3z. 4x will add with 5y and 6z. And then 7x will add with 8y and 9z. And remember, that's equal to this vector here, which is this vector over here. And so as a system of equations, this actually means that if two vectors, by the way, again, this is 3 rows, but only 1 column, because 1x plus 2y plus 3z is just a single number, that has to equal 7. The second row has to equal the second row. The third row has to equal the third row in order for two vectors to be equal to each other. So if we remove the brackets now and we write it in what's called scalar form, this is just now our system of equations that was being represented as a matrix equation up here. So let's practice this a little bit. Write the system of differential equations dx dt equals 3x plus 2y and dy dt equals 2x minus 4y as a matrix equation. So the first thing I'm going to do is I'm going to write these two equations above one another. like this. And now I'm going to wrap them with, I'm basically working backwards from where we ended up in our little example here. So now I'll put some parentheses around these to say this is a 2 by 1 vector equals another 2 by 1 vector. And now what I can do is I can actually think about lifting, again, working in complete reverse. We can now split this apart into the vector 3x, 2x, plus the vector 2y, negative 4y. And then we can factor out an x from the first vector. We can factor out a y from the second vector. And now we can, again, work backwards where in this step, from here to here, we conducted the multiplication. So if we were to sort of think about this x, y, and z as lifting back up into the x, y, z vector, the analogy here would be that the x, y lift back up into an x, y vector. And before those columns got scaled, they were part of a matrix with 3, 2 as the first column and 2, negative 4 as the second column. So our final answer here to write this in matrix form would be to say that the vector dx dt, dy dt equals 3, 2, 2, negative 4 times xy. And it's going to be important to actually write a system of equations in the matrix form because we're going to be doing something with this matrix here. Again, this matrix that contains all of the coefficients. This is just called the coefficient matrix. Sometimes you'll see this, that's really the derivative matrix. You'll see it often written like this, dx dt. So it's the derivative of a vector. We'll talk more about that soon. And then we'll just call this here the x vector. That is the vector without the derivatives of x and y in it. So a lot of times you'll see this written as dx, a system written as dx dt equals this coefficient matrix. Usually people write capital Y times the vector x.